So hello, everyone. My name is Lingyuan Liu. I'm currently a postdoc at IES. Today it's my honor to introduce Monica Vazirani to give the third talk of our mini course, Representation Theory, Combinatorics of Symmetric Group and Related Structures.
Yeah, welcome back for the third lecture, day 4. Or maybe it's day 6, since we'll count Saturday and Sunday. Let me go a little bit more in depth into some things that I mentioned in the last lecture, which involve this picture. This is Young's lattice of partitions. Right, this is something that you can get an elementary school student to draw once you explain the rules to them. That, for instance, if you have a partition of 5, that means you have 3 plus 2, and I like to draw my partitions English style. Uh-oh. You hear the echo now? I was hearing an echo before, but I don't hear one now. Is it from me? My voice is echoing?
Yeah, I guess it's solved.
Yeah, great. I closed my Sakako. Yeah. All right. So yeah, right. So I like to draw so you put the biggest number at the top and upper and left justify everything. So there's this kind of origin everything's going from. And then we do we put an edge here because going from the 4th to the 5th level, if I line up the origins, this diagram sits inside of the other one. So combinatorially, this is quite easy to generate, but representation theoretically, it means a lot. It captures more than you might imagine about the symmetric group, and in fact, other algebras as well. And so I had mentioned last time that these edges that we draw, that combinatorially are just about one diagram sitting inside the next, that these edges encode the functors of induction and restriction, depending on whether we think of looking at what's happening in this direction or what's happening in this direction, going from 4 to 5 boxes or 5 to 4 boxes. Yes, and then that's what the edges are. And the nodes, each one stands for an irreducible representation of Sn, if I have n boxes. Okay. So there were some questions about that, so let me go in that in slightly more detail. Okay, and also let me say from once we have this graph, some extra information that we get about the symmetric group. All right, so the nodes are these partitions of n. You can still see them at the top of the screen, 7 partitions of 5, and for each node, we have an irreducible or simple Sn module. Now, the edges, as I mentioned, tell you about restriction. So for instance, if I take the restriction of the simple module corresponding to the guy I have on the bottom is 4, 2. And so I would be restricting from S6 to S5. The reason I have an edge between S4, 1 to the reason I have an edge from 4, 1 to 4, 2 here is precisely because S4, 1 occurs in the restriction of S4, 2. Okay, and another way to say that it occurs is to look at the dimension of this Hom space, right? And we kind of learn that from characters as well when we were looking at Schur's lemma and so on and so forth. And one of the amazing things that happen is when there's a non-zero space there. In other words, when this S4, 1 occurs as a sub in the restriction, it occurs exactly once, okay, not twice. So I refer to that 1 as being multiplicity free. I could call it multiplicity 1, but I'll call it multiplicity free. Okay. And again, everything's semi-simple, so it occurs as a direct summand as well as just a submodule. Okay. So more precisely, right? let's compute the entire restriction. So if you want to compute the entire restriction, you need to look back at the graph and think, what are all of the edges coming out of this? Okay. Or you can simply look at this partition. Let me just try it twice here. And if you think about what are all the diagrams that sit inside of here but have one fewer box, that's the same thing as saying, what kind of box could I check out and still have what's left be a partition with that same origin? Okay, so we could check out this box, or we could check out that box. So that's another way without having to draw the whole lattice to see what lies above. Okay, and I might call this guy removable. And then we'll get the modules indexed by that, and we'll do the direct sum of that. Now, something that I like to do is, going from S6 to S5 is nice because 5 is smaller than 6. But, if we were thinking, for instance, in terms of these diagrams that we have with morphisms and such, if you think about having 6 dots versus 5 dots, that's a little imbalanced. So I like to often record that there's a 5, 1, that I have this parabolic subgroup that I'm restricting to that has, that still sums up to 6. And then you'd say, well, is there any difference between that restriction? And in some sense, no. But it's actually convenient to keep track for other parts of math connected to this that we might not talk about at all this week, but for my research, I like to keep track of it. And so I would actually explain what I'm doing in the picture in a second. One, two, three, four, 5. Okay. So remember that S51 is isomorphic to S5 cross S1, and S1 is just the trivial group. So the representation is the trivial group. There was just that one singleton box. There's only that one partition. But a representation of a direct product of groups looks like this kind of outer tensor product of these vector spaces. So, okay, I'm tensoring with a one-dimensional vector space. What's a trivial action? There's really no difference. Well, they're different, sorry. They're isomorphic, but they're actually different, okay? And so I like to keep track of that, even though I won't in the rest of today's lecture. Okay, now, we also mentioned last lecture, or we've mentioned many times, that induction and restriction are adjoint functors. And so once we completely understand the restrictions of all of our irreducibles, we understand all the inductions as well. And so if I induce from, let's pick 3, 2, and there's 5 boxes in there, so we'll have to induce from 5 to 6. Again, I just need to look back at Young's lattice and see what lies below this. But in the same way that I don't have to draw the lattice above, I could just think about what partitions of 6 contain 3, 2, is to just draw this picture and think about what are the boxes that I could add and still have a partition with that same origin. And let me not, since the red is they're X'd out above, let me kind of color these to note they're filled in here. Okay, and so we get the direct sum of these 3. Okay, and again, it's multiplicity free. Whatever does occur, they're distinct and they each occur once. And there's many things that don't occur. All right. All right, so now I'm going to convince you that one of the interesting things that we get off of this graph is not just that we've parameterized all the irreducibles, we can do something like count their dimensions. Okay, so why can we now count the dimensions? A lot of you have seen this before, but if you haven't, I'll try to explain. that in the lattice, you just have to count, for instance, if I want the dimension of this simple S31, I just have to go back to the graph and count all the paths that start at the top node, the empty set, all the way to this partition 3, 2. Okay, and you always go down, 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 down. You're always adding a box at each step. Okay, and so why should that be? Well, if you believe in the branching rule, right, I take this representation, and if I restrict it from 5 to 4, I have to get rid of this box and I get 3, 1, or I can get rid of this box and I get 2, 2. Now, that means that this vector space is the direct sum of these two vector spaces, and we saw that dimensions add. So that means the dimension of my starting representation is the sum of the dimensions of these next two. And I got lazy about writing the S's everywhere, so I'm just going to write the shape. Okay, but now we can keep going, right? We know how to restrict this from 4 to 3, and we know how to restrict this from 4 to 3. Okay. Okay. And so here we go. And so that means that whatever this dimension is, it's the sum of these dimensions, and this one happens to be the same. Okay, and now I keep going. I restrict each of these from 3 boxes to 2, and the dimensions will add. And then I have to restrict each of these from 2 boxes to 1, and the dimensions add. And of course, there's really nowhere that you need to go after 1. You could go to 0 to the field, but let's not, because this guy is one-dimensional. Okay, and there's no, it's one-dimensional and it's unambiguous which representation of S1 it is. There's only one simple there. Okay, yes, these are also one-dimensional, but that's sort of coincidental. Let's really go down to where everything is one-dimensional in the name. Okay, and so that means that the dimension, what I started with is when I restrict all the way down to the trivial group, I get these 5 different copies, and so the dimension is 5. And now if I unravel what I did, if we unravel what we did, so for instance, why is that a path? For instance, let me take this particular one-dimensional subspace I just created, okay? Because actually it's more than just a path. I'm actually picking out a specific vector in here, right? So this one came from this one up here, okay? And where did that come from? It came from up here, right? And where did that one come from? It came from this one, right? There's a choice. There's a choice as I follow all of these branchings down, right? I have to keep track of where everything came from. And this one came from here, right? Which is over here, which sat inside of here. All right, that seems a bit fast. So let's look at it on just one big picture, right? Right, so my choices was exactly the choices that I'm showing here. That, that second one in the list as I chose my branches is really first getting rid of this box, then getting rid of this box, which means on this edge, then getting rid of this box on this edge. And I chose getting rid of this box, so it's this edge. I don't really have a choice here and here. Okay. So for each of these paths, I'm picking a specific one-dimensional subspace in here. And at the end, I've got just a direct sum of one-dimensional subspaces. So the number of them is my dimension. Okay. And let's see. So we've just shown, right? So we've just shown that the dimension of the simple indexed by this shape is the number of paths. Well, we can reverse it and always start at the empty set and go down, or we can start at the bottom and go up. But let me say they all go down starting from the empty set, so that for any shape, we'll always start at the same place when we do our count. Another really nice gadget that we have, for instance, if we then were to do this, say, for even a larger partition, it can be a little bit annoying to have to draw this whole graph and to actually count the paths and keep track of them all. So we encode this in what's called a standard Young tableau. Okay, and that means we just have to draw the shape and we fill in it with the numbers that gave us our choices of when did we add each box, right? So I've already actually filled in here for each of these blue edges. I just put the number in the box of I added it, and the number is when did I add it. Okay. And so you'll see, right, I always have to add the corner box first. I'm not allowed to add a box below with the origin up here. And then I filled them in 2, 3, 4, 5, 2, 3, 4, 5. So, yeah. So my abbreviation I'll use today is SYT for standard Young tableau. And I'll put the lambda there if the shape is lambda, in this case 3, 2. Okay. So in other words, the number of paths that gave our dimension, it's also the number of standard Young tableau of that shape. So that's really nice. Right, so just what I had said in words, written out. So to get a standard Young tableau, if you have n boxes, you fill 1 through n in the boxes, and they have to increase across the rows and decrease down the columns for the way I draw my diagrams. I'm going to call this number f lambda, this number of standard Young tableau, which is the same as the number of paths, which we just showed with the dimension. Okay, right? And in summary, why again is that the dimension? Because if you restrict your representation, say from S5 all the way down to S1, or you can think of it as 1, 1, 1, 1, 1, the only choice we get is this particular one-dimensional one. I guess I really should have put it just a 1 here because I put 1 box. And it occurs with some multiplicity, and that multiplicity is the number of paths, but it's clearly also the dimension. So if you've written it the direct sum of one-dimensional spaces. But part of why this works, that got a little bit swept under the rug, is that we have this multiplicity-free branching. I mean, it's that our Young's lattice is actually correct, but right, this multiplicity freeness really let the combinatorics come through and let this be this nice, easy formula that you don't have to, you don't have to worry about having multiplicity. Another thing that's really underlying this is, 1 by 1 matrices are commutative, but 2 by 2 and 3 by 3 and 4 by 4 are not. Okay, so this multiplicity one is very special, and I haven't proved it, right? I basically proved if you have the right picture that this formulation works, but I haven't proved, I haven't actually proved that the branching graph is correct and it's multiplicity free, and I'm not going to prove that today. Okay, it takes a little bit more work and knowledge about the representations. Okay, and of course we also use sort of the transitivity of restriction, that you can restrict and restrict and restrict again, or restrict all at once. So, so by transitivity, right, restrict, 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 restrict. Okay, so as I said, that gives you more than the dimension, that gives you an actual basis, right? These one-dimensional spaces, we count the number of them, we get the dimension, but these are actual one-dimensional spaces. That means we actually have a basis up to scaling, right? How do I know I have this one-dimensional subspace? I could take any vector in it, or 5 times that vector, or negative 3 halves times that vector. So it's more or less a basis up to rescaling. Okay, and you might want to call this a Gelfand-Cetlin basis. This is compatible with restriction. I guess there's other names one could call it, but this basis that we pop out, it's compatible with restriction, whether we go from n to n minus 1, or n all the way down to 1, or to anywhere in between. So hopefully that's clear. Okay. So here's this wonderful basis, and I want to show you a different way to get the same basis. Okay, that's also wonderful algebraically. Oh, sorry. But before I do that, I'm not going to spend that much time on this, but it's really worth mentioning because, it's good to learn some cool math, and this is just really cool, even though I'm not going to prove it, okay? Which is this number 5, this number of paths we had to count. Or for instance, if I went to the partition 4, 2, there would be 9. And, this path counting, if it's a really big partition, That's a lot of paths to count. Or it's a lot of standard Young tableau to count. It's really easy to miss one. Isn't there some nice formula that would just tell me the dimension? Yes, it's called the hook length formula. And what you do is, if you have a partition of 5, you put 5, 4, 3, 2, 1, 5 factorial upstairs. And then you divide by certain 5 numbers. Okay, in the same way you might, like with the binomial coefficient, right? You divide by 5 factorial over, something, something, instead of 5 numbers. What 5 numbers do you take? They're called the hook lengths of your partition. And so it is not a tableau. It is, you look at a box and then you say, let me go out to the edge as far as possible and down to the bottom as far as possible. And that's called the hook of this box. And oh, there's 1, 2, 3, 4 in the hook. That's why I put a 4 here. Okay. Or there's 2 in this hook. These removable guys always have hook length 1. And there's 2 in here. And if I take those numbers and let's just check, right? So I arrange them in there, but they're in the denominator, right? The 4 and the 4 cancel. Oh wait, something went wrong. Because that's not a 2, that's a 3. Nobody caught that. 3, sorry, because there's actually 3 in that hook. Great. And then the 3 and the 3 and the 2 and the 2, and you're left with 5. That's a lot easier than counting the standard Young tableau, just dividing some strings of numbers. So let's check here. The 5 and the 5, the 4 and the 4 and the 2 and the 2. Oh, and this 2. See, it doesn't have to cancel exactly. There can be some funky division there, but 3 times 3 is 9. And I actually did check. You have 9 standard tableau. Okay. And proofs of this, there's many proofs of this, and like they're all wonderful, and they're worth reading about on your own. I'm sure Sagan has some in there. Okay, so that's a really, really cool fact to take away from here. All right, so let's recap where we are. So when we have Young's lattice, on the combinatorial side, we just have the nodes. On the representation theory side, we have one irreducible representation or one simple module for each of those nodes. And they're arranged by S1, S2, S3, and so on. The edges tell me when I take the restriction of the bigger representation and I restrict from Sn plus 1, say, to Sn. If this occurs as a submodule, it's detecting that, and the multiplicity is 1. Okay, and also I didn't just say it occurs as a submodule, I wrote it at the dim of a Hom space to connect it to some of the things we did in last lecture, but also when you generalize this to other settings or characteristic P, or if you're in a not semi-simple place, this is the kind of statement you want to look at. And we just saw that if you do if you want to get the dimension of that module combinatorially, you just count paths. So for instance, I took a much easier partition here, 2, 1. There's 1, 2 paths. Okay. All right. Well, are there other things we can see from this lattice? Is there other kinds of counting we can do? Because we love counting. Those of us who love combinatorics, even if you don't love combinatorics, there's some kinds of counting I think that everybody loves. Okay. So what if I don't just, I go to this guy and I turn back, or I go to this guy and I turn back. But I also might allow myself to go somewhere else and turn back. So in other words, I want to count loops that start from the empty set. They go down to some destination, say 3 edges away, but then they come back. Let's say I want to count that. And why would I want to count that? Well, we'll see why. Okay. And we'll come to this other counting in a bit. Right. So, right, for instance, on this picture, right, let's say I want to have all loops starting from the empty set going to the 3rd level and coming back. So I could go like this and I could come back. I could go like this and I could come back. Right. I could go like this and I could come back. I could go like this and I could come back. But you could also go like this and come back the other way, or you could go down this edge and come back the other way. Well, that's very messy. Okay, but if you think about it, how many paths did I go up and down? 1 plus 2 squared, because 2 is that dimension, plus 1, that adds up to 6. And 6 is also 3 factorial. Okay. And I claim that's what you'll always get. You'll get n factorial if you look at all loops that do n downs followed by n ups that follow the edges. So why should that be the case? Of course, we already know how to get n factorial in many other ways, but why should that be the case? Well, n factorial is the dimension of the symmetric group. Sorry, it's the size of the symmetric group, so it's the dimension of the group algebra. And you might remember from representation theory that the size of the group is also the sum of the dimension squared of all your irreducible representations. And the reason that's true is because this is a semi-simple ring. Art and Wedderburn says it's the direct product of matrix algebras. So the dimension of each of these matrix algebras is the dimension of an irreducible representation. But the dimension of a matrix algebra is the size squared. So that's where these squares come from. So in other words, I should put it in here. Right, so what I'm saying is that the sum of these f lambda squareds over lambda being partitions of n is always going to be n factorial. F lambda squared, right, that gives me loops because I go down and then I come back up. So, right, I had like 2 ways to get down to 2, 1, and therefore I also have 2 ways to get back up. So hence 2 squared. Okay. So that's some fun counting. Now, what if I say, well, okay, I had loops of size of length 2n, length of 2n steps that went from the empty set back to itself, but it's a little artificial, isn't it, to have a loop that always goes down and then always comes back up. Maybe I just want loops that have to take 2n steps. And of course, it has to be an even number of steps if you're going to start and end at the same place. So what if I just take all loops from there to there? Wouldn't that feel more like what you do in topology, right? Yeah, so what happens then? And let's try to look at that count. Well, first of all, we have to decide how our ups and downs are going, okay? So for instance, let's see. Yeah, I'll just draw a little piece of it here. Right? At step 1, you can only go down then up. There's only one way to do it. But if n is 2, right? First of all, there's the ones that go down, down, and up, up. So that we already know is n factorial. But now that we're allowed to go up and down in any order, we could go down, up, and we could get that extra path there. Okay. Now you can't go up first because there's nowhere to go up. Okay. And so the choices of up downs, there's Catalan numbered many of those because downs and ups are kind of like parenthesizations, right? Which is Catalan numbers. Okay. And the fact that there's nowhere to go above the empty set is this condition of why it's a Catalan number and not some other way of just rearranging. It's not like 2n choose n. It's a different number to divide. Okay. But then, you know, still there's, but how many ways are there to do this? Well, if you go down to n equals 3, well, you get to do this in the exercises if you want. But again, your choices of up downs as a Catalan many, but then there's going to be, well, 3 factorial here, some number, some number, some number, some number there. It's going to add up to something. And why might you do this? Well, spoiler alert, maybe shut your ears if you want to work on the exercise and not have any hints. But if you add these all up, the different ways there are that I'm not going to tell you, you get 15. And then you say, I would like to look, and then you say, well, 1, 3, 15, I'm not sure what's going on there. So let's say you went to n equals, 4. And then the number you get if you would factor it would be 1 times 3 times 5 times 7, or 7 times 15, whatever that is. And you would say, ah, maybe that's the pattern. 1, 3 is, and 3 is 1 times 3. And then the 15 is 1 times 3 times 5. And the next is 1 times 3 times 5 times 7. You say, ah, I think I see the pattern. Okay. And then you also say, wait, I think I've seen these numbers before, maybe in Katerina's lectures. Where have we seen them? It's the dimension of some algebra. And that shouldn't be so surprising, right? We've got n factorial when our loops all went down, 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 then up, up, up. The size of the symmetric group, right? The dimension of the group value of the symmetric group. So that this should be the dimension of an algebra. Should maybe not be that surprising to you that, oh, whoops, let's see. Yeah, that I'll come back to this later. It should be the dimension of the Brouwer algebra. So let's just check on a small example. If we're just matching, 1 dot and 1 dot into 1, do we really get 3 if we're matching at n equals 2? Yeah, there's 3 ways to do these matchings. Remember, with Brouwer's, you're allowed crossings or cupcaps. And then you're like, wait, are there really 15 if I do it on 3? And you can start counting and you can say, huh, I don't know, I gave myself room for 15. Is it really so? And you can check in the exercises that, I left room for 3 factorial up here. And then if you organize it well, you might indeed find these extra ones that you're looking for over here. Okay. All right, and that means that this graph, this branching graph for Young's lattice, has something to do with the Brouwer algebra as well, and has something to do with induction and restriction potentially there, okay, that you can think about. And let me also say that if we're talking about the temporally Lieb algebra, which you've seen in Katerina's course, the underlying graph is way simpler than Young's lattice. It really just looks like a number line of positive numbers or non-negative numbers. But by the way that things are unoriented, remember with the Brouwer diagram, your strands are unoriented. Temporally Lieb, they're unoriented, meaning you allow caps, or you're not like walled Brouwer. But, oops, VPN's trying again. Sorry, with the symmetric group, we thought of everything as always pointing up, which is part of why we always had to go down, 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 up, up, up. But we don't have to here. And so in this graph, you're allowed to have, loops going up and down, and that's why Catalan number is the full-on dimension here. Okay, so I'll let you think about why this picture gives you that the dimensions here are Catalan numbers. All right, now let's return to the basis that we constructed. Okay. And I'm only going to look at the basis for the symmetric group, not for Brouwer algebra or for temporally Lieb algebra that you might get by doing these path countings. Okay. So we had this particular basis that was compatible with restricting in these ways, this way of splitting up the diagram and then following how you're chopping up your vector space. And so I'm going to get this basis in a very different seeming way, which is by using a commuting family of operators, okay, in the group algebra of the symmetric group. And one thing you might remember from linear algebra, if you have 2 matrices that commute with each other, and if they're both diagonalizable, they're simultaneously diagonalizable, right? So for one matrix, you can find a basis of eigenvectors. And for 2 of them, you can have a common basis of eigenvectors. And so I am going to realize this wonderful basis that we get from repeated restriction as actually common eigenvectors for a bunch of commuting operators. And these operators are the favorite ones we like to use, are called symmetry operators. Now, a lot of times people just hand you these operators and say, here they are. And they don't always tell you where they came from. So I'm going to tell you also 2 ways, if I have enough time, of thinking of where they come from, or at least how I think about them. All right, and the first one I think you see less often in the literature. So let's connect it to the exercises that we all did in the afternoon session. So let me think about the conjugacy class of transpositions in the symmetric group. And let me take the element in the group algebra that's the sum of all of the transpositions. Okay, so there's n choose 2 of them. I've written them in cycle notation because that's a little bit easier for a transposition, but I could write them in one line notation, or I could draw my diagram for it. You just swap 2 entries in all the possible ways that you can. Okay. Now, also, we were reminded in lecture that this element is central because it's constant on conjugacy classes. And if you want, you can go back and do that exercise if you're not sure why. And because it followed from Schur's lemma, because this element is in the center, it has to act as a scalar on any given irreducible representation, but maybe different scalars on different representations, maybe the same, but by a scalar matrix, a multiple of the identity. So certainly this guy can be diagonalized, right? It's just one big scalar matrix. And what is that scalar? Well, if you have the character table, or you do the exercises, or you just think about transpositions, you can compute the scalars. And so let's take this little piece of our branching graph. And I claim the scalar, so I would look at C5 in the center of S5, acting on this simple for S5, C2. And I would just compute that C5 axis 2 on this. Up here on this level, these are S4 representations. So I care about has C4 acts, C4 axis 2 on this one, and axis 0 on this one. Okay. And what's going on? What's the pattern? And why do I care about the scalar? Well, I'm going to fill the boxes of lambda. So first we filled them with numbers to make standard tableau. Then we filled them with hook length. Now I'm going to fill them with contents. So all of these different ways we filled the boxes of lambda have been very separate from each other. So it's easy to get them confused if you haven't seen before. Now I'm going to fill them with the contents, which is I'm just really filling it with what diagonal it's on. So the main diagonal is 0, and then I go up from there. So like, jth row minus ith column. Okay, and now having done that, I can read off of this content filling these scalars of the central element that's built from transposition acts. I just sum up the contents. Okay, so for instance, how did I get the C4 axis 2? I look here for how to label my diagonals, and I say, oh, I always label the main diagonal as 0, and then I go from there. So 0, 1, 2, and minus 1, 0, 1, minus 1, and 0, 0, 1, 2, minus 1, and 0. And if I want to know that C4 axis 2, I just have to add up these 4 numbers and hope I get 2, add up these 4 numbers and get 0, whereas here I add up these 5 numbers and I get 2. And that is a combinatorial rule for how this central element acts. Okay, I didn't prove why, but it's true. And it can be computed from what we know about the symmetric group. Okay. Now, I claim that this information is actually like enough to recreate everything I've said so far and recreate this basis with a little extra work. So similar to this miracle that gave us great combinatorics, that the restriction of an irreducible representation for Sn to Sn minus 1 was multiplicity free. The central, so Cn acts by just some big scalar here, but Cn minus 1 is acting on scalars on all the irreducible pieces here, the irreducible summands, and Cn sort of separates them. It's acting by different scalars on each of those pieces. And because Cn minus 1 separates the summands, so does the difference Cn minus 1. And that difference is a Jusis-Murphy operator. Okay, so what is that difference? Well, remember Cn was the sum of all transpositions in Sn. And this is the sum of all transpositions in Sn minus 1. So if you get rid of all of those, the only ones that you have left over, right? So you had the A's and the B's where A was less than or equal to B was less than n minus 1. You're going to see all of those occurring unless B is actually equal to your n, and it will be these transpositions. So that's your Jucis-Murphy element. And again, what's great about it is that it detects in the restriction how everything chops up. In other words, if you restricted from your favorite representation, say from S5 to S4, and let's say you didn't already know your basis that was compatible with restriction, all you'd have to do is look at this Jucis-Murphy operator and look at its eigenspaces. And there would be, the 0 eigenspace and the 2 eigenspace, and they would be, 3-dimensional, 2-dimensional respectively. And one would be this, 3-1 diagram that we see, and the other would be the 2-2 diagram, which is going to be compatible with that restriction by this separating. All right, so to write more concretely than just this formula, let's just see, right? So for n equals 1, we don't have any transposition. That's just 0. For n equals 2, we have a single transposition, 1, 2. Right? For n equals 3, again, we don't take all transpositions. We just take transpositions of things that swap with 3. So 1, 3 plus 2, 3. The fourth Jucis-Murphy operator, right? Swap 1, 4, swap 2, 4, swap 3, 4. The sum of all transpositions where you contain 4 is one of the things you swap. Okay, and so on and so forth. And so you can just talk about these Jucis-Murphy operators kind of on their own. When you write it in cycle notation, I'm not telling you whether this lives in the group algebra of S5 or it lives in the group algebra of S27. It can live wherever you need it to live. So I could say, look, this lives in the group algebra of S3 and this lives in the group algebra of S4 and so on. Or I could say, hey, all of these guys all live in the group algebra of S5 all at once, whatever I need to do it for. But for today, it's going to be helpful to pick an n and then say, these are all going to live and say the group algebra S5 all at once. Okay. All right. And so, yeah, and so by using this idea that we did with the branching, and if you believe me about the Cn minus 1 is enough to separate, I'm hopefully going to try to convince you that the basis that we get is really an eigenbasis or a weight basis for the Jucis-Murphy operators, and that they really separate them out, that the weight spaces will all be one-dimensional. Okay. Did I hear a question? Okay, so let's just see it in action, right? So here's my partition 3, 2. Here's my basis. I've decided to use this trick of write standard Young tableau, giving me my basis that's compatible with restriction. Okay, and I've divided them up compatible with restriction from 5 to 4. And how have I done that, right? If I get rid of the 5 box on these 3, they all give me the 3, 1 partition. And so this is the first step in chopping up my vector space. Whereas how do I get the 2, 2? Those are the things in my basis that all first remove the 5 in that box. Okay. So again, that's what I mean by how I get this basis. I'm looking at the order of what I'm removing. I'm looking at successive restrictions and successive chopping up my vector space. But, whoops, typo. So the Jucis, oh no, was not a typo. Sorry. So before we asked how the central element acted, now we're just looking at the difference of the central elements. So I claim if we go back and unravel that, it's saying the Jucis-Murphy operator here is acting as 0. The Jucis-Murphy operator here is acting as 2. Well, again, if you believe my rule that the central element acts as the sum of the contents, the reason that the Jucis-Murphy operator is acting as 0 is that I label my diagonals, my contents, and it's because the 5 is on the 0 diagonal of all of these, and that tells me the 5th Jucis-Murphy element acts as 0. Whereas here, The 5 I remove is on the second diagonal. That's telling me my Juices-Murphy operator 5 acts as the scalar 2 on those. Okay, so again, I get these two blocks of how the Juices-Murphy operator acts, compatible with restriction. Eigenvalue 2 on this piece that corresponds to the 2, irreducible. Eigenvalue 0 on this piece that corresponds to this 3, 1 of irreducible. This also motivates people to refine restriction with something we can call I restriction, which packages this in here. So don't just restrict from 3, 2, from S5 to S4 and get the partition 3, 1 or the partition 2, 2. Land on exactly one partition using these eigenvalues to separate you. So you could say, look, I restriction is going to give me the piece where the nth Juices-Murphy operator acts by the scalar I. And I happens to be an integer always in this case. But there's other settings where you have analogs of these, where instead of an I, maybe it's a q to the I. Maybe it's something a little funkier. Or maybe it's I mod p if we're in characteristic p. Okay. So the functor of restriction breaks up into the direct sum of these I restrictions. It's I running through integers. Okay. And these I restriction operators, you can look at relations between them and you can just study them on their own. And they give you the avenues to seeing that the symmetric group categorifies not just symmetric functions, but categorifies a certain representation, say, of SL infinity. By looking at these operators, they act by basically Chevalier generators on a particular representation. I'm not expecting non-experts to understand any of the sentences, but just to connect it for that. So, and again, why does this work? The reason this works is because, as you can practice in the exercise, this Juices-Murphy operator, JMN, commutes with all things in Sn minus 1. Okay? So that because it commutes with that, its eigenspaces are preserved by Sn minus 1. Okay? So that tells you this refinement can be done. All right. Yeah. So for instance, we can take the 2 restriction or the 0 restriction to get these two pieces. It separates them out. And in the same way that restriction is multiplicity free, I restriction is multiplicity 1. Okay, or could be 0. All right, so this is multiplicity 1 phenomenon, and which tells you wonderful combinatorics can be harvested. All right. So let's put this together and see what I mean by saying that this is a weight or an eigenbasis. Okay. So, all right, let's look at, say, I don't know, this first basis vector, right? We said to understand how the 5th Juices-Murphy operator acts, we just look for what diagonal it's on. Okay, I have to cheat and put my diagonals in over here. And the 5, right, is on diagonal 0. So talking about JM5, 5 here. So maybe it helps to actually do the following. Let's superimpose. We'll go 0, 1, 2, minus 1, 0. And then let me put in the tableau, 1, 2, 3, 4, 5. Okay. And so the 5th operator acts as 0. That means the 4th operator is going to act as minus 1. The 3rd operator is going to act as 2. The 2nd will act as 1. And the 1st will act as 0. Okay. And if you remember, the first Juices-Murphy operator was 0. So it had better act as 0 everywhere. And it does, because 1 is always in the first box. Okay, so in this way, you can figure out the eigenvalues of all of these Jusis-Murphy operators on my basis, which I chose to be compatible with restriction. Okay? And the fact that we get eigenvectors shouldn't be that surprising, given everything above. Okay. Now, if you think about it, right, these numbers here, well, they're not all distinct from each other. I have 2 zeros. But there's certain rules for how the 1, 2, 3, 4, and 5 are allowed to live in here. Okay. And if you write it out and you put here the whole spectrum, this whole 5 tuple for how all the Jusis-Murphy operators act, right? Okay, well, this one acts identically as 0. But again, these guys commute with each other. But how did I know they would be diagonalizable? I mean, they'd be simultaneously diagonalizable if they're diagonalizable. Well, if you look at each of these 5 tuples, they're distinct as 5 tuples. Okay? And that comes from the fact that we take all standard tableau and there's certain, it doesn't matter that there's repeats on the diagonal because you'll never have something that goes like 1, 2 and be standard on a diagonal. So you'll get these distinct spectrum. In other words, you'll have these one-dimensional weight spaces. And so part of why they're simultaneously diagonalizable is because they have distinct spectrum. So if you wanted to study this from scratch, you could invent a Jusis-Murphy operator, start looking at their spectrum on irreducible, and you could prove that it would have simple spectrum on an irreducible. And so that would tell you that all the weight spaces are one-dimensional. You could prove that, and you could get this wonderful basis in this way. Okay, and then if you looked at the combinatorics, well, I'm always seeing these numbers, a 0, a 1, a 2, a -1, and a 0, but they're permuted in some ways. What's going on with the different valid ways of how these numbers are permuted in each column? You would reinvent standard Young tableau. The combinatorics are the same combinatorics as standard Young tableau, even if you didn't know they were there to begin with. And again, the fact that they could be simultaneously diagonalized is like saying when I have a matrix with distinct eigenvalues, it can be diagonalized. So you don't have distinctness taking just one operator, but you have distinctness if you take all 5. Okay, so really nice linear algebra. Right, okay, so if I say call script J, the commutative subalgebra in the group algebra symmetric group generated by all the JMI. So let's say if I run, say, between 1 and n, then this is sitting inside the group algebra. That's n. Right, so now if I restrict not doing S5 to S4 to S3 to S2 to S1, if I just restrict to this commutative subalgebra J, my irreducible representation breaks up into a direct sum of one-dimensional representations of J, and it's multiplicity free. Okay, so again, wonderful combinatorics. And it is my Gelfand-Cetlin basis. It is the basis compatible with restriction. So this is a second way of getting the basis. And that's really nice. Getting a basis as eigenvectors of operators is really nice, especially if you have some inner product floating around. And if these operators happen to be self-adjoint, or if you have good control over what their adjoints are, having an eigenbasis for a family of self-adjoint operators means that that eigenbasis is going to be orthogonal for that inner product with respect to their adjoints. And that can be really handy. In fact, if you look at Macdonald polynomials and how do you prove that you're constructing Macdonald polynomials the way Zrednik did them, he used this fact. He looked at a bunch of commuting operators acting on a space, and he looked at the adjoints, and so he said, okay, my eigenfunctions for them will be orthogonal, and Macdonald polynomials were characterized by orthogonality and triangularity. Okay? And the triangularity comes from somewhere else. So that's a little aside for the experts. Okay. Now, yes, so as I mentioned, if we just studied the combinatorics of the weights for this subalgebra J, you would rediscover standard Young tableau and branching weights. So, let's see. Yes. diagrammatics. Oh no, there's only 3 minutes left. Okay. So let me talk a little bit about diagrammatics. So if you try to draw the Jusis-Murphy operators and you're in the symmetric group, it's not that exciting. But as we kind of saw in Laura Ryder's talk, if you move to the Hecke algebra first, you put in this Q in this extra structure, you can learn a lot. Okay. And I do recommend, if you skipped her talk, to go back and watch the recording. So I claim that, so we saw these in the exercises from Katerina's course. I might have drawn them a little bit differently. You can take these operators that take the ith strand and kind of wrap it around and come back. If you do that, they're very related to the Jusis-Murphy operators. And I should say, another way of drawing this. So remember my Jusis-Murphy operators was the difference of two central elements. You can actually take it the difference of something that just encircles a bunch of strands and encircles a bunch of strands. And just for normalization conditions, I had to put a little extra kink in there. Okay, so you can practice the exercise if you want, going between these diagrams. And I claim that if you take this xi and subtract off the identity, and then subtract q minus q inverse, so you resolve these crossings to make these sums of reduced looking pictures, you'll get the Jusis-Murphy operators drawn with positive crossings. So that's in an exercise. So if that doesn't make sense, do the exercise and read the exercise. Or let me just show you on an example. So x2 takes the second strand and wraps it around. And I'm saying subtract off the identity, then divide by q minus q inverse. Well, this picture, if it was in the symmetric group, it wouldn't be reduced. It would just look at the identity. So let's resolve this crossing using my local relation. It'll cross in the other direction, which means it can smooth out and just become the identity and cancel. Or it can go, you follow the arrows up and it smooths out this way, which if I undo that, it just looks like this, which looks like crossing 1 and 2, which is the first Jusis-Murphy operator. Right. So likewise, if I took the third strand and pulled it around, I would get the sum of things that looked like my 1, 3 plus 2, 3. Okay, up to the fact that things are over and under crossing. Okay. And let me just check. Okay. Oh, right. And then, so where do these pictures come from? You could say, well, I was happy with that sort of Cn minus 1 picture. But the real place where I think of them coming from is that, yeah, you can take the ice, you can put this on a cylinder. We can go to the affine world or the annular world on a cylinder or on an annulus. You can take the ice strand and you can wrap it around the cylinder. And that lives well in the affine world. But again, we're not living in the affine world, we're in the finite world. But if we push it down to the finite world, we just fill in the cylinder. We pretend it's not actually a genus, that it doesn't give us any pi 1. And then if you say, okay, if I wrap this around the cylinder and I redraw it, this up to this extra little kink that I had to normalize by is, it does look something like this or something like this. Okay, if I am allowed to collapse the cylinder. And so these operators, and that they commute and that they have nice spectrum in the annular affine world, for me is where Jusis-Murphy operators really come from. That they come from these X's, they live in the annular world, and we just have this homomorphism that pushes us down to the finite world by filling in there. Okay, and I think that is probably, yeah, whoops. Okay, that's probably a good place to stop.
Let's first thank Monica for the wonderful talk. And are there any questions?
Oh, and don't forget for Slido, I don't know if anybody has the Slido link handy to remind to please post questions in there within 2 hours after Katerina's lecture ends.
I guess I have a sort of naive question. If you look at the complement of the tableau within the rectangle, like if you complete it and look at the corresponding hook lengths, does that give you anything interesting or no?
Oh my goodness. Let's see. So let's say we take, so you want to take a tableau like this, and then make a rectangle and look at the complement. And then you're looking at the hook length of inside the complement.
Right.
You would put like a 1 there, or let me do like a slightly. So let's say if we had something like this, you would like make a rectangle like so, and you would put in hook lengths here like, oh my goodness. Yeah, you would have like 4, 3, 2, 3, 2, 1, kind of going up like that way. Is that how you would put the hook lengths in?
I would guess so. Yeah. Yeah.
Okay. I'm not sure. Yeah, I'm not sure. So taking the complement in a rectangle, and of course you have the choice, right, of choosing what's the height of that rectangle. Maybe it's like so. So if you look at something called Schur-Weil duality, which is connecting the representation of the symmetric group to that of the general linear group or special linear group, there, the Young diagrams correspond to weights, highest weights, finite dimensional representations, and then the complement in a rectangle, depending on what the height of the rectangle is, can be giving you the highest weight of the dual representation. And then, of course, the hook lengths for that are telling you, for instance, for the hook length formula, telling something about the dimension with the dual. But I'm not sure. And of course, in general, the size, the number of boxes in the complement can be far different from the number of boxes in the original. And so, yeah, I'm not sure when you're looking at this for that dual relative to GL, what those numbers mean. Yeah, I'm not sure for the complement. I've never thought about it. I will say for the original diagram and its hook length, there's not just the hook length formula. It also is telling you things about there's a bilinear form on your irreducibles, and it's giving you information about it, which actually, when you go to characteristic P, is very useful. For instance, you can read from those hook lengths whether when you go to characteristic P, do you stay projective or do you stay irreducible or not? It has to do, it's telling you something about the radical of the form that you have. And I should mention, for those of you who love Sagan, the way that Sagan, I forgot to say this, the way that Sagan builds his basis, but the way that Sagan builds a basis of the irreducible representation using standard Young tableau is completely different from what I talked about today. That's using tabloids and tableau, and it's taking sums in some very different way, and it's looking at minimal idempotence in a very different way. And it's giving you a different basis. His basis works well over the integers. It's integral. It's set to do characteristic P for you. This way of having these commuting operators and taking their eigenbasis, it fails miserably in characteristic P. Well, not miserably, but there's a lot of it that doesn't work in characteristic P. You have denominators floating around somewhere that you couldn't see in what I was doing that give you trouble in characteristic P. Sorry, I went off on a tangent from your question. Interesting question. I don't know the answer. If someone else knows, maybe they can say or put in the chat and arrange to meet and talk later.
Thank you.
There's a question in the chat by Sarah D. Browner. Is there some generalization of Druce's Murphy elements of Coxeter groups? If so, do they have similar representation and theoretical properties?
Well, let's see. So for type B, there's a way of seeing type B as a quotient of one of these annular or affine, say Hecke algebras, right? You can go from the annular or the affine to the type B Coxeter group. And so you could just have the similar picture and get operators there. I'm not sure. So for the classical families, you could do something. For something like E6, E7, E8, I very much use the fact, and I meant to say that I very much use the fact that, S4 is contained in S5, is contained in S6, and so on, right? This branching graph, we had to understand all these different levels, and we can move between them. if you take some other Coxeter group that's all by itself, you don't have this wonderful tower to appeal to. And for me, that's a lot of where the structure is coming from. But, you know, A, B, C, D do occur in these infinite families. And so I'm not sure if there's a well-developed theory, you know, all on its own, but you could, you know, you could do something like take something like a central element that was a conjugacy class sum that made sense to all the towers, and you could look at relative differences and get commuting operators that way. Maybe other people who are better on literature know about what the usual generalizations of Juices-Murphy operators are in the BCD case.
I mean, I think it's general. It's like exactly what you just said. For these towers, you start at the base and then you take the differences, because the what you're doing is those central elements act like nested elements of the centralizer algebra kind of thing, and so the differences will pairwise commute.
Thanks, Aj.
Thank you.
Monica, if you could just repeat, because I needed a reminder about this. You said that self-adjoint operators, if you simultaneously diagonalize them, then the basis is orthogonal, the eigenbasis is orthogonal. Is that what you said?
Yeah, so if I have, let's see, so if we just, you know, let me say this, right? So if we have like AV is lambda V, and you know, but like AW is mu W, I'm gonna just do this, right? And if you sort of look at V paired with W, you can say, okay, up to a scalar, you know, okay, really we should be Hermitian and blah, 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 blah. But you can be like, okay, you know, you can compare this. What do I want to say? Oh yeah, that's not what I want to do. Right, if you look at AV paired with W, that should be V paired with A adjoint W, right? And so this is going to give you lambda V paired with W. And well, if A is self-adjoint, then this will be VAW, and then you're like, aha, that's V mu W. And you're like, wait a minute, either lambda has to be equal to mu, but it's not, or you have to have, so then you have to have V paired with W being 0. So it's just the analog of this fact. Yeah, but of course now my pairing, so maybe I really need to put a complex conjugate there if I'm being Hermitian because it's in the second factor. But yeah, so this is the basic fact that when you have a self-adjoint operator, its eigenvectors for distinct eigenvalues will be orthogonal. And again, what happens in McDonald polynomial land is, you know, these operators aren't necessarily self-adjoint, but they're adjoints. You understand what they are in terms of other operators that are similar. And so you know the eigenvalues and you know you have some kind of distinctness and you're still able to prove orthogonality. Yeah.
Monica, why lambda cannot be mu? Can you just have an eigenvalue?
Oh, I'm saying if. Yeah.
Okay.
If lambda is not mu, then yeah, so if you take eigenvectors for distinct eigenvalues, yeah, so either, yeah, so if they're different, then is that, or I could have said, you know, lambda has to equal mu, or these guys have to be 0. That's another way of saying it.
Okay, thanks.
Linear algebra is the best. Everything comes down to linear algebra.
Are there any other questions? So,
Sorry, can I ask a question? So what's the advantage of going through this commutative subalgebra route? Since you already had all that information from the Young lattice, why do you go with the Juicy-Murphy?
Yeah, that's a great question. Let's see. I guess because sometimes you live in situations where you don't have something like Young's lattice. Like, you know, with double affine Hecke algebras, you don't necessarily have one nested in the other. I guess these operators are totally interesting to study within their own right. People have had lots of success categorifying them. And also the fact that they're, yeah, as operators, you know, they're these I restrictions that we get out of them, that they're categorifying something going on with other interesting algebras, that as functors, looking at them and their endomorphisms is very worthwhile, is very interesting. Let's see. Yeah, maybe for just the symmetric group in characteristic 0, you don't necessarily learn anything new, but it's still a rich perspective to have. But it leads to lots of other mathematics just because there's so much wonderful structure there. I might have to think more about your question and give you a better answer later.
Okay, but this was also good, thank you.
You also see the symmetric functions inside of the group algebra of the symmetric group as like the central characters sort of living inside of there as symmetric functions in the UC's Murphy elements. So short functions and things like that living inside the group algebra.
Yeah, really good point. Something that which I mean, I should give everyone a break for. But if you take a symmetric polynomial, you know, not just the sum. If I took, you know, the third symmetric function on the third elementary symmetric function on the Jesus-Murphy operators, or a power sum symmetric function, or so on, these guys would actually live in the center of the group algebra. And so they would act by scalars. And so that's, yeah, refers to what, you know, enforces what Zad was saying about central characters.
In
Okay.
that,
Oh, sorry.
I was just gonna add that, like, for me, the UC-Murphy element, it also gives like it gives more sense on why you are getting the tableaus. So you can also go from the UC-Murphy element and actually prove that you have the Young lattice, and that is like, it's like, what are the vertices, and that is like having only one arrow and those things. So it's kind of like the first time I saw representation theory of the symmetric group was with the Sagan approach, and it was like, but why do you have tableaus on those things? If you try to do it like from scratch using the UC-Murphy element, it's way more like natural.
Yeah, I totally agree. I totally agree that if you just kind of said, organize this data usefully, you would just reinvent this picture. I should stop though, because we need to get started with better.
Let's thank Monica again.